So what we're going to do is create something we call force diagrams. Basically, you end up with a box or anything. Sometimes you'll see them and it's just a dot. That dot or that box is meant to be the object at where the forces are being applied. So you can draw a fancy object, something like very descriptive of what the object is, or you could just put a box. It does not matter. So we tend to look at the forces in four directions: up, down, left, right. Right now we have a book at rest on a table. Like I said, this is not a fancy drawing. The book has a weight of 15 newtons. So we put a dot in the middle and we draw our arrows from that central dot. The weight of 15 newtons, that is a force, and that is pointing downward. So I'm going to put 15 newtons here. Now, there's this part that says the table holds the book up with equal force. Now, you might not have ever thought about this, but if the object is not traveling downward, then there must be an equal force pointing upwards to keep this balanced. And you know this from experience. If you put a book or something on a table, it doesn't crash through the table, it sits there. So if the weight is pushing down, there's another force that pushes up with the same value. So this is the book pushing on the table is the 15 newtons downward, and the table pushing back on the book is 15 newtons upward. We call that force upward the normal force. That normal force comes right from the surface where an object is sitting. So, are there any pushes occurring with this object? Is it being pushed left or right? No. So you could just leave them, or you could put arrows saying 0 newtons, because there is no push to the left, there is no push to the right. So you could put that. When we say the net force is the overall force once everything cancels. So 0 and 0 obviously cancel because they're zeros. But what about 15? So there's 15 newtons upward and 15 newtons downward. Because they're in opposite directions, they actually cancel. The net force right here is 0 newtons. If there was a force, we would put the value of the force and we would put the direction, because force should have a direction. We would say blank newtons up, down, left, or right. Acceleration and force are directly related. So if there is no force, there is no acceleration. The acceleration would also be 0 meters per second squared. And now there's one more question, and that is, are the forces balanced? And we would say the forces on this, oh my goodness, I'm sorry, I misspelled forces. Balanced force, question mark. We would say yes, the forces are balanced because the net force is 0 newtons. If the net force was anything other than 0 newtons, we would say that this is not balanced. And that means that a force is winning, a force is pushing in one direction. All right, here we have a second example. A box with a weight of 50 newtons is being pushed to the right with a force of 60 newtons. The ground is pushing up on the box with a force of 50 newtons, and there is friction opposing the motion with a force of 20 newtons. So let's put these in. There's 50 newtons downward, that is the weight. Every object will have a weight component. Now, as we said, the box is not crushing through the ground, so there must be an equal but opposite force going from the ground back to the box. That is also 50 newtons. The box is being pushed to the right with a force of 60 newtons, so the rightward arrow is 60 newtons, pushed to the right. Now, when we say opposing the motion, forces like friction or air resistance oppose the motion of the object. So if the object is moving to the right, the frictional force works against it. It's trying to keep it from moving. So the 20 newtons is actually left. The 20 newtons will go right there. So now I go back to my same two questions. What is the net force? And are the forces balanced? And the net force in this case, the 50 and the 50, the up and the down, are equal but opposite, so the 50s will cancel. But the 20 and the 60 do not cancel. So yes, we're pushing with 60 newtons, but there's 20 newtons of resistance. So the actual movement is only caused by 40 newtons of force. I would subtract those. 40 newtons of force, and then I do have to specify the directions. 40 newtons to the right. Are they balanced in this case? No, they are not, because the net force is not 0. So as long as that net force is not 0, the forces are not balanced. If the forces are not balanced, there is acceleration. Now we're going to go one step further with this. How can we figure out how fast this is moving? Our formula is force is equal to mass times acceleration. Now, what do we know about the object? Do we know the force? Do we know the mass? Do we know the acceleration? Well, we know the net force. We don't know the mass of the object, but we can figure it out using this formula. If weight is equal to mass times gravity, and the object has the gravitational acceleration of 9.81, then we can work backwards and figure this out. So we have mass being equal to weight divided by gravity, which would be 50 newtons divided by 9.81 meters per second squared. And we can calculate that and get a value. So if you divide 50 and 9.81, we get a value of 5.1 kilograms. Now the same thing will happen here. Let me push this upward a little bit. We have force is equal to mass times acceleration. We know the net force. We know the mass. We want to find the acceleration. So we would rewrite this formula. So force equals mass times acceleration is going to get rewritten to solve for acceleration. So divide the mass on both sides. So acceleration is equal to the force divided by the mass. And remember, the force is the net force. Net force. That's the overall force. So the overall force of that box that is acting on it is going to be the 40 newtons to the right. And then the mass of that box is 5.1 kilograms. If we divide those two, we will get a value of 7.8 meters per second squared. And we're going to specify 7.8 meters per second squared to the right, because the net force was to the right. So this box, if all of these forces are applied on it at the same time, will begin to move with an acceleration of 7.8 meters per second squared to the right. We have to get the net force by canceling out all of the extra forces. Like we said, the 50s all cancel. The extra 20 subtracts from the 60. We figure out the mass of the object by taking the weight divided by 9.81, and we use that to figure out what the acceleration of that box would be.